Okay, part two, the celestial sphere. Now, what do we see when we look up at the sky, the nighttime sky? If we look at it, it appears to be almost like a hemisphere, almost like a half of a sphere. And again, objects that we see in the nighttime sky are so distant from us, we can't use our binocular vision. We can't judge distances. Therefore, we get the sense that it's a hemisphere. And in fact, the idea of the heavens, the celestial sphere, dates back to the ancient Greek philosophers who believed that it was actually made of crystalline spheres. And heavenly bodies were thought to move on these spheres, and it was almost like a mechanical system of these rotating spheres that would cause the cycles of the celestial objects and the planets that we see. We use the model of the celestial sphere to represent the nighttime sky, but we understand that this is not actually reality. It does appear to be a sphere to us, where we can see the top part of the sphere, and the other part of the sphere will be hidden below the horizon. And as the sphere rotates, objects will come in and out of our view. Now, celestial coordinates allow us to describe the position on this imaginary sphere. We can use something called altitude and azimuth to represent where an object is in the nighttime sky. Altitude is the angle between a horizon, if the horizon is represented by no topography. Of course, if we have mountains or if we have buildings, that will raise the horizon a little bit. But if we have no topography around us, altitude would be the angle between the horizon and the object. Azimuth represents the angle between a particular direction, usually north, and where the object is. So it allows us to represent on this two-dimensional surface where an object is located. Altitude and azimuth are really not good coordinate systems for objects in the nighttime sky because they only tell us where an object would be at a particular time. Okay? These objects are moving. As the Earth actually rotates on its axis, as the Earth moves around the sun, these objects will change their position. The most important motion of the Earth, of course, is the rotation on its axis. Approximately once every 24 hours, it rotates, and this causes the objects, which are much more distant from us, to also appear to move. It's very much like if you're driving in a car. You see objects outside the window, and they appear to move past you. They are not actually in motion, at least not with respect to the surface of the Earth. You are in motion, and because of your motion, they appear to move. Same thing here. The Earth is rotating on its axis, and because it's doing so, objects such as stars, planets, the sun, the moon also appear to move. However, think about the rotation of the Earth. As the Earth spins on its axis, it's rotating about two poles. It's rotating about the North and South Pole, or it's rotating about an axis that passes through the North and South Pole. So if we extend this whole idea of the nighttime sky moving because the Earth rotates, we can understand this motion as being due to the rotation of the Earth on its axis, which makes the sky appear to rotate on its axis. Now, extending from the Earth the concept of the North and South Pole, we also have a North and South celestial pole. At our latitude, approximately 41 degrees north, we can only see the North celestial pole, and we can see some of the southern half of the celestial sphere. Celestial South Pole can't be viewed unless you're below the equator, unless you're south of the equator. Okay? So we would see or perceive the sky to rotate about the North celestial pole, and in fact, objects would rise exactly east if they're sitting on the celestial equator and set exactly in the west, again being on the equator. Now, for the nighttime sky, we do have coordinates that match the movement of the Earth. And these are called bright ascension and declination. Declination is the angle that an object makes with respect to the equator. So all the stars sitting on the celestial equator, all the stars that are immediately above the Earth's own equator, would have 0 degrees declination. The north celestial pole is at 90 degrees from the equator, just like our geographic North Pole and equator. So declination really describes how far north or how close to the north celestial pole an object is. Right ascension is a little more complicated. Right ascension is not measured in degrees, not typically. Usually it's measured in hours, minutes, and seconds. And the reason for that is as the imaginary celestial sphere rotates, okay, it takes about 24 hours to complete one rotation. Thus, objects are given coordinates that are associated with time, how far they are from what is called the vernal equinox, the place where the sun is on the celestial equator when spring first begins. So we can describe the coordinate system of different objects, and they'll never change for stars. They will change for planets and will change for the sun and the moon. With regard to these coordinates, right ascension and declination. If we look at the nighttime sky, from our location here in Jersey City, we have a very difficult time seeing some of the less bright stars. Many people believe that the North Star is the brightest star in the sky. It's not even close, okay? In fact, in Jersey City, I've had a very difficult time even locating the North Star, also known as Polaris, also known as Ursa Minor, Alpha Ursa Minor, because it's only roughly a magnitude 1 star. If we watch the nighttime sky, what we actually see is all the stars will rotate about, or appear to rotate about, Polaris, or the North Star, and the North Star never changes its position. That means that the North Star is very, very important for navigation, okay? It never changes its location. It's always over exactly due north. And therefore, in navigation, it always was a very good source of direction. The stars surrounding Polaris actually never rise and never set. They always stay above the horizon. We call these circumpolar stars. Now, circumpolar stars are really a function of your latitude. If you are at the North Pole, be standing on an ice pack at this time of the year, Polaris is exactly overhead, and all of the stars in the northern hemisphere are circumpolar. At our location, 41 degrees north, only the stars, okay, that are 41 degrees from Polaris are going to be circumpolar. At our location, we have Ursa Minor, what we call the Little Bear, which has the asterism, the Little Dipper, that's circumpolar. The Big Dipper, which is an asterism found in Ursa Major, is also circumpolar. Cassiopeia is an easy one to see. Cephas, Draco, and part of Lynx. Camelopardalis is actually a giraffe that's also visible. Now, this is a motion picture of Polaris, and you can see all the stars moving. And what we notice is the stars very close to Polaris hardly move in the same time period. As we go further and further from Polaris, we notice greater and greater movement. You even captured a meteor in this particular image. Let's stop there, and I'll pick up on the next video of the sun.